Okay, so yeah, okay. Good morning and good afternoon, everybody. Thank you joining the I²CNER seminar series. So the I²CNER seminar series was launched in 2010 upon the inception of I²CNER Center. Since then, seminar series has featured the best researchers in the world on carbon neutral energy issues. So I'm Chihaya Adachi from Kyushu University Opera, and so I will host today. So today we welcome Professor Angus Rockett. So everybody know Angus very well, I guess. So, but I shortly introduce him. The Angus is the professor of the Department of Metallurgy and Materials Engineering at Colorado School of Mines and emeritus professor in the Department of Material Science and Engineering at the University of Illinois. So he was the president in 2011 and is the fellow of American Vacuum Society. And he was the general chair of the I²CNER Photovoltaics Specialist Conference in 2016 and has held many positions in both PV, SV, and AVS. So his research involves defects in semiconductors, primarily focused synthesis and the characterization of solar cell materials and theory and modeling of solar cell materials. So I heard he published more than 170 papers and also gave a talk more than 140. So he's very a great contribution in these societies. Okay, if Petros can speak, can you please give a greeting? If not, maybe we can start Angus' talk.
Okay, thank you very much. It's a tremendous honor to be invited to give a talk at this seminar series. And I have very much enjoyed all of my interactions with you all. So thank you once again. I want to say thank you also to the people listed on this slide who are the students, postdocs, and others who worked with me over the years and have helped me do a lot of the research that I've accomplished. It's been funded by the US Department of Energy and the National Science Foundation, as well as the I²CNER Center at Kyushu. So thank you so much for everything. Of course, you all know that renewable energy is a carbon-free source of energy that's growing fast worldwide from its humble beginnings with a few small solar cells here and there to massive installations of solar today. And I'll show you some statistics. I'm going to talk a little bit about renewable energy in general as we get started so that you have a context. I hope that it will be of interest to you and that I don't tell you too much that you already know, but if I do, I apologize. So here's a nice little chart that was recently published by Nancy Hagel and Sarah Kurtz at the US National Renewable Energy Laboratory, where they have done a study of energy generation globally. And so the top row here is global energy generation in terawatt hours divided up by various technologies. The second row is the rated capacity of the various generating sources in terawatts, or it's a pie chart, so it doesn't really matter. But the thing that's interesting about this, if you look at it, is that there's a difference in the amount of capacity, for example, for solar and wind compared to how much is actually deployed, how much is actually generated. And that's because solar and wind don't function 24 hours a day, whereas nuclear power, you can see there's a much larger pie wedge for nuclear in the generated area than in the capacity area, because you run a nuclear power plant as much as you can. However, global installed capacity is increasing much faster in solar and wind than any of the other technologies. There's a modest increase in hydropower, a larger increase in fossil fuels, and a little tiny bit of increase in nuclear. although decommissioning of nuclear plants is actually happening faster than installation. So solar energy is really growing, so is wind. And the International Energy Association agency has forecast growth in the future, looking out, in this case, 5 years at what's coming along. And they forecast that renewable energy, primarily wind and solar, will meet 99% of increase in global energy demand in the next 5 years. So they're not talking about the total energy demand, but they're talking about the increase and meeting 99% of that. It's more striking in the EU and the United Kingdom, where the increase in renewables is forecast to be 9 times the increase in energy demand, which means that the new installed technology is replacing coal primarily. If we look in the US, the increase is about 3 times the increase in demand, and it's replacing primarily coal and nuclear power. They indicate that demand is growing much faster in China, and renewables will only meet 65% of it there. And the ASEAN nations, they call out separately and indicate that most of it is fossil fuel in that case. There is a note here about the report for Japan. If you'd like to look that up, that will show you the changes that IEA forecasts specifically for Japan. So one thing that I want to take note of is the fact that this scale goes up to only 200 gigawatts of annual installed capacity additions. And at 200 gigawatts per year, it's going to take a really long time to replace all of the fossil fuel technology worldwide. However, things are changing. Wind and photovoltaics are expected to dominate the world's new installed technology by mid-2024. And the forecast for the International Energy Agency shows that installed capacity for wind and photovoltaics will dominate the other technologies probably by 2024 or so. And in the US, it's expected to dominate by about 2030. I see a note in the chat that says, would I share my slides? I believe that the presentation is being recorded. If you can't see my slides currently, please let me know. But I'll be happy to share the slides from this talk. So one of the things that really, I think, puts this into context is the change in the United States, and this has been the case for a number of years now. Retired capacity is mostly in the area of coal, and new added capacity has been dominated by natural gas, as shown on the previous slide, wind and photovoltaics, but there's also decommissioned natural gas generation. If you take that into account, then natural gas is only growing at a modest rate, lower than either photovoltaics or wind this year. And so, at least in the United States, photovoltaics is growing very rapidly, consistent with this observation for world capacity. I'm going to focus this talk on photovoltaics as a result, but things seem to be a little different in Japan, and I would love to have somebody correct me. I was looking at the various forecasts and so forth, and again, this is from the US Energy Information Administration. So it may not be correct, but it seems to be consistent with the numbers that I got from reports from the various Japanese agencies. And so if we look at the history, as maybe is not too surprising, natural gas and petroleum are dropping off. Coal is dropping off a little bit in Japan. Nuclear went through a hiccup after the Fukushima accident. But as of 2019, there were reported to be 62 gigawatts of photovoltaics installed in Japan, and the breakdown of installed capacity is shown on the left, with basically an equal number of nuclear, hydropower, and solar. Relatively little wind, and predominantly fossil fuels of one sort or another. So if we look again at that chart, or the goal for Japan is 22 to 24% renewables by 2030. If we look at the chart that I had up earlier and sort of put this in context, the goal for Japan for 2030 is shown here from a report, the projection from 2015, with a large increase in nuclear capacity and basically some modest increases in solar and hydropower. It's interesting because nuclear is significantly less than 20 to 22% at the moment. Renewables are currently at 17% of electricity generating capacity in Japan, and forecast to increase to 22 to 24%. So it's really not that big a change. And this seems to have been repeated in the Japan Energy 2020 report, but I saw a rumor that the sixth strategic energy plan may include more photovoltaics and wind. And that would be much more consistent with the sort of increases in generating capacity elsewhere in the world. And of course, you all are masters of photovoltaics, so I'm sure that there is technology in Japan to do this. One of the things that I think we all know about photovoltaics and wind is that storage is critical. And at least in the US, their power is heavily discounted, which means that you can't sell the power for what you can sell other kinds of power for, because you have to either use or lose the power from wind and solar. So the people who buy it know that you have to sell it, so they don't pay as much for it. So it would be great to have energy storage. Currently, I think the main methods are batteries and pumped hydropower, pumping water up a mountain. And battery technology has been improving. I think we've all seen electric vehicles coming along. I know that Toyota has increased its focus on fully battery-powered pluggable electric vehicles in the past few years. And the lithium-ion batteries are dominating the technology. This is US data, but I think it's consistent with Japan. And the cost is dropping dramatically along the way. So batteries are getting less expensive, and this is going to help photovoltaics tremendously. Energy storage can be divided into either energy or power, and a lot of battery storage systems these days are focused mostly on power. So because they're not very large systems, they're intended to cover short bursts of demand. So a photovoltaic array that's putting out power, the batteries might be used, for example, to cover a cloud going by or something like that. Whereas energy storage focuses more on extended supply, the equivalent of a conventional generator, and there's been so much work going on at I²CNER on hydrogen. I think that's a great technology for the future, along with things like pumped hydropower. There is a report from MITI on status and needs where they cite the need for lower cost energy in Japan to strengthen the energy grid, the electric power grid, and I think we need that everywhere. That would be a huge benefit in all parts of the world. They need demand flexibility, and they've outlined ways of doing that, and an interactive system that controls bulk power production at large central facilities versus distributed generation. They talk about pumped hydro for energy storage, and they talk about lithium-ion batteries, currently with about 3 gigawatt hours of installed capacity in Japan. I think hydrogen is an alternative, an excellent alternative to battery storage, in particular because you can tell the state of charge of your storage system, which is very difficult with batteries. So that's a little bit of an overview of where I see renewable energies in in the context of energy globally. And at this point, I'm going to switch gears and focus in on photovoltaics. And for anybody who's not familiar with the photovoltaics challenge, I've got a couple of slides here on what constitutes competitive success in photovoltaics. And the first is that your manufacturing process has to be fast. It has to be very, very inexpensive. It's nothing like doing microelectronics or something like that. It has to be efficient and it has to be reliable. So what do I mean by these? Well, fast, if you have an expensive piece of equipment, you need to pass a solar module through it in about 10 minutes. So you'd better be able to make a solar module about every 10 minutes or less in an expensive tool, because that's the only way that you can make it inexpensive enough. You'd better be able to manufacture your product for about 40 US cents per watt. And we specify the performance of a solar module in terms of rated standard watts under standard conditions, rather than how it would be for you, because your sunlight may vary, temperatures vary, and so forth. So this is a standard test condition, and all of the current products are selling on the range of 40 cents per watt or so. It's not clear that anybody can make money doing that, but that's the current going price. To be competitive over the long term, you probably better be making 20% efficient modules. And as I'll note, the silicon community is certainly doing that. And it needs to be reliable, which means very low maintenance over the next 20 years. So these are very difficult challenges to meet. So when we think about what are the key requirements and why is efficiency a key requirement, module costs, the solar modules that you can buy these days are a tiny fraction of the cost of systems, especially large systems these days. You can buy commercial products for 50 cents per watt, 50 US cents per watt, which is a very low price. It means that you can get all of the solar modules that a house would need for maybe a few thousand US dollars. So really what it comes down to is that efficiency is the key. And that's what's driving all of the research these days. The reason for this is because most of the costs of a solar array scale with area and not with power. So when you think about what goes into a solar module, there's the glass, there's the frame that holds it in place, there's the shipping, the wires that connect it, and in particular, these guys up on the roof who are installing the solar modules turn out to cost quite a lot. And so the more efficient we can make our solar module, the less of all of that stuff we need. So a guy up on the roof installing a module, if it makes 200 watts, it costs a certain amount. If it makes 300 watts, that guy's labor costs a lot less. So it's all about efficiency. So no talk about solar cells would be complete without showing you the NREL efficiency chart for single junction champion cells. And I'm only going to talk about a small part of these. I'm going to talk about silicon. I'm going to talk about the hybrid perovskites. I'll talk about cadmium telluride in the yellow, and I'll talk about copper-indium diselenide in the green. That's not to say that other technologies aren't interesting, but I have limited time, so I'm going to focus. So here is a sort of a chart of the family tree of solar cells, and they divide into so-called one sun devices and concentrators, and I'm not going to say much about concentrators, but that's a system where there's a lens that focuses a lot of light on a small solar cell. So I'm not going to talk about the polycrystal and silicon technologies because those have mostly been replaced by single crystals. I'm not going to talk about amorphous silicon because it largely is not competitive these days because of efficiencies. I am not going to talk about much about the single crystal fancy 3.5 devices because those are mostly used for space applications, and they're too expensive for the Earth. Dye-sensitized and organic devices are interesting materials, but because of time, I'm not going to talk much about them. And I'm not going to talk much about concentrators. So I'm going to focus the rest of this talk on single crystal silicon, and in particular, the perovskites. I'll spend more time on those, cadmium telluride, and copper indium diselenide. So let's think at the beginning about the potential of each of these technologies, and who is the efficiency leader in real products. So silicon, you can buy products. I note the SunPower modules at in excess of 22%. There are many silicon manufacturers worldwide that will sell you a module with more than 20% efficiency. So that really sets the competitive challenge. Copper indium gallium diselenide, Japan is famous for that, and in particular, the Solar Frontier company is making modules. They list their product at 13.8% efficiency. So it has some ways to go in terms of improving performance, but it's a very interesting technology. Cadmium telluride, the first solar series 6 modules are specified at 18.2%. And what you'll notice from this, there also are hybrid perovskites coming along. I'll talk about those, but there's no product yet. What you may notice about this is this challenge of 22% efficiency with silicon, and that's really what is the problem. So I'm going to look to begin with at the potential of each of these technologies and a couple of others, and then we'll look in more detail at some of the interesting research challenges for each one. So I mentioned concentrators. I'll just show you an example of a concentrator system. This is a very large structure. An automobile would be down here at the bottom somewhere. And so a very large object, it requires a lot of complex machinery, because when you have a lens focusing a lot of light on a small solar cell, as the sun moves across the sky, you have to turn your array to face the sun continuously, which means it's very mechanically complex. And it requires a lot of machinery, a lot of materials. And while this seemed like a really good idea because you could make extremely efficient solar cells, it turns out it's not very competitive economically on the ground. The so-called 3.5 materials, things like gallium arsenide, are very good if you make a device with several solar cells stacked up, a so-called multijunction. You can get complete solar cells, systems of solar cells that are at least 35% efficient, which is too expensive to use on Earth considering the competition, but it is used for space applications because for space-based systems, you're more concerned about weight than you are about expense. And so you're willing to pay a lot more for an extremely efficient device that you can put up on orbit for less weight. So that's all I'm going to say about these two technologies, and I'll be happy to talk more at the end if you have questions. But I'm going to turn to some of these big competitive technologies. And of course, silicon is by far the major technology worldwide. And that's disappointing because silicon is very well known and there's much less to study about it. It matches the cadmium telluride modules in cost, and it wins on efficiency currently. But cadmium telluride has a lot more opportunity to improve. Silicon, of course, benefits from a long research history, including a lot of work in the microelectronics industry. And one of the things that's really clear about silicon is that it's a simple material with very few native defects. So you can have dislocations, you can have vacancies and things like that. but it's nothing like the compound semiconductors in terms of native defects that you have in it. So it's a very easy material to work with, a very easy material to optimize. And when you have a problem, you can often turn to the rest of the literature to see what's going on. Thin film technologies, and I'll just mention that this array here is a copper indium gallium diselenide array from Solibro. I had this when I lived in Illinois. For all of the thin films, efficiency is a challenge in module scale. Cadmium telluride is why our photovoltaics are inexpensive today. So in about 2005, First Solar Company said, you know what, we can make our product for $1 per watt. Silicon was selling for about $4 per watt at that time. And so Silicon said, well, we can do $1 per watt. And they matched the cost of cadmium telluride. And at the same time, First Solar said, well, we can do 60 cents per watt. And Silicon took a deep breath and said, we can do 60 cents per watt as well. First Solar said, you know what, we can do 50 cents. And so it has gone to the point where we've gotten down to about 40 cents a watt. First Solar is still making money at 40 cents per watt. The silicon community struggles because that's right on the edge of what they can manage. And it's very difficult for First Solar as well. But 40 cents per watt is the current sort of wholesale rate. So cadmium telluride has been responsible for a lot of the price drop and a lot of the increase in the market worldwide. For copper indium diselenide, I think there's still hope, and we've had some exciting results lately that I'll talk about in regard to that. And then there are the other thin films. In particular, I note the hybrid perovskites, which are, I think everyone agrees, the most exciting thing around. But stability is an issue. We have to figure out how to make these things stay highly efficient over time. And I'll mention a couple of issues, a couple of experiments about that. Organic photovoltaics have always faced challenges. In particular, so-called exciton binding energies, the free negative charges and the free positive charges tend to stick to each other too well in organic materials because their dielectric constants are relatively low. And so that's been a challenge, but there have been some really exciting developments in organic photovoltaics lately. The modules remain relatively low efficiency, but there's still opportunities for improvement there. So that's a quick tour of some of the major technologies. I'm going to mention some research opportunities now and a few things that are going on with each of these. So one of the problems for silicon is that the champion device, the best small device that's been made with silicon, is 26.7% efficient. And that's very close to the theoretical limit. So there's real questions about whether you can improve silicon in a champion device at this point. People have been saying that for a while, and they've still managed to make improvements, but this is getting very close to the real theoretical limit. So what can we do? Well, one of the things that you find with silicon is that when you run a silicon solar cell, you tend to have so-called potential-induced degradation, and that's often related to complexes of boron and oxygen. And this is in particular when you have a so-called P-type silicon wafer. So one approach to dealing with this is to change to N-type silicon wafers that you build the devices out of. But there are advantages and simplifications when you use a P-type wafer. Boron-oxygen complexes are very well known. They've been a well-known problem in silicon technologies of all sorts for many, many years, and they remain a problem to figure out how to deal with. So that's one of the major research problems in silicon. There is a significant opportunity in multijunctions. And I'll just mention a little bit about multijunctions. The schematic at the bottom here shows the solar spectrum from the red side of the spectrum to the blue side of the spectrum, from low energy to high energy. And so this is what sunlight looks like if we make a solar cell that has a semiconductor with an energy gap in, let's say, the energy between the blue and the green. We lose use of all of the other photons below that energy. They just go right through the material because it's transparent. So we get a lot of energy out of the blue part of the spectrum, but we don't get much current. And so if we move our junction down to a lower energy, we get more current, but we lose voltage. The ideal voltage, the ideal semiconductor band gap is around 1.4 electron volts, but that has limitations, and silicon is much too low. So what we're going to do is we're going to stack solar cells on top of each other. We're going to have one solar cell that catches the blue light, maybe another one. If we had a 4-junction cell, one would catch the green light, one would catch the yellow, and one would catch the red light. So the theoretical limit to efficiency, if you had an ideal band gap around 1.4 electron volts, you could get to 37% efficiency. And that's important because that's about where cadmium telluride is. So our current efficiency in cadmium telluride is limited, and it has a lot of opportunity to improve. We should be able to almost double the efficiency of a cadmium telluride solar cell with more research. A 2-junction cell could achieve 50% efficiency, and that's really where silicon has an opportunity. And if you went totally crazy and you had an ideal set of 36 junctions, you could get to perhaps 72%. There are 6-junction solar cells that have been made in these very high efficiency space-based solar technologies. They're in the range of 45, 47% efficient. So the thing about multi-junctions is that with a small additional cost, I can make 2 solar cells instead of 1, have a large gain in efficiency with relatively little additional cost if I can make a good solar cell in the blue part of the spectrum. So that top so-called wide gap cell needs to be the best, and it needs to be very good. It's also unfortunate because that's the hardest junction to make a good solar cell out of. Well, this has been done with silicon in conjunction with these so-called perovskite materials that I'll mention a little more about. And so this particular example was reported in 2016. The efficiency of this device is not that good. It's about 16% in a tandem. The remarkable thing is that recently there was a record device produced of 29.5%. So a couple of percent more efficient than silicon, one of the best tandem device performances around. And this is a silicon perovskite combination. So this is a real challenge. It's going to probably challenge every other solar technology out there if you can make silicon perovskite tandem. So that's really your challenge. And this is a great research opportunity if you're good at making perovskite devices and if you can make them stable. Cadmium telluride has a lot of different questions. One of them is, why is the voltage so low? We should be able to get a lot more voltage out of a cadmium telluride solar cell. People are looking at alloys of cadmium selenide telluride, and that gives you the opportunity to adjust the band gap a little bit and potentially make a better performing device. We need to increase the p-type doping in the cadmium telluride because that's one of the problems that you have with this material is it's hard to dope. We'd like to look at alternate heterojunctions. The current cadmium sulfide technology is not very attractive, and people are looking at zinc magnesium oxide, but they've had a lot of trouble with that. And that's an opportunity for you to do research on, looking at improved back contacts in the devices. And I'll just give you an example of one of the ideas I've had for studying this. And that's to make a bipolar junction transistor out of the device rather than trying to make a solar cell. So a solar cell, you try to make an ohmic contact at the back. A bipolar junction transistor, you try to make a junction on both sides. And the nice thing about a bipolar junction transistor is that you can diagnose a lot of different things with it. So for example, if we run it as a phototransistor and shine light on it, we can diagnose the recombination rate, and we can adjust the photon wavelength to control that recombination rate. We can also adjust the so-called collector bias, the reverse bias junction, and understand about carrier diffusion because we can adjust this depletion width on one side of the device, and therefore we can collect carriers from the middle differently depending on that reverse bias, and we can study that dynamically. We can also look at the so-called emitter junction and look at emitter efficiency, and that will tell us about recombination of the holes at that junction. So I think it's an interesting opportunity. If we work on it more, we can look at things like so-called gain bandwidth product, and that will tell us how fast we collect carriers to the different sides. It'll tell us about true mobility in the material. There are research opportunities as well in copper indium gallium diselenide, and I'm sure Solar Frontier would be very happy to have you solve problems for them. In these materials, the voltage is again low relative to where it should be because there's too much recombination of carriers in the device. We'd like a faster deposition process, and I mentioned the fact that you need to have very little time in an expensive process. And so in terms of, we need a faster way of depositing the material. I'll show you an example of how my group attacked that problem. We need optimized treatments because it turns out that alkali metals help the materials, and we need to figure out how to improve that. We'd really like to make a wide gap device, and the current devices are narrow gap by comparison. They're very similar to silicon. So we'd really like to have something like copper gallium diselenide or a sulfur compound to get a wider gap material. So just to show you a research example, what we've been looking at, I mentioned that speed is really important in the process tool. One of the ways that devices are made, although not how Solar Frontier makes theirs, is a so-called three-stage deposition process. So what we've done is we've increased our deposition rate by a factor of 10, turned down our temperature by 200 degrees C. We get pretty lousy material, and it's shown here in this SEM image. And what we've shown is that if we interrupt that deposition process and with just a few minutes of deposition of silver bromide, look at how much better this crystal structure is in this bottom material. We have huge grains in the material compared to little tiny grains in the reference material. It makes a much better solar cell. Okay, so this is very similar to the so-called cadmium chloride process that the cadmium telluride people use. It's part of the reason why the cadmium telluride devices are good. We took this copper indium gallium diselenide solar cell that's 14.8% efficient. We post-deposition treated it with potassium fluoride, with rubidium chloride, and so forth. We got this up over 16% efficient. And we haven't spent a lot of time working on these materials. So that's copper indium gallium diselenide. We've also looked at the hybrid perovskite materials, and I'll mention a couple of examples there. The questions are many. What controls stability? And if we improve the stability, how can we do that without loss of efficiency? Because a lot of the time, if you improve the efficiency, you do so, or stability, you do so by substituting other things in the perovskite structure, which may not work as well. We'd like to look at alternate absorber materials to see if we can do better with something else, some other form of hybrid perovskite material. We need to look at the materials that go into the device, which is to say alternate hole and electron transporting materials. And we need to improve the modules to match the cells. So our record solar cell is about 27% efficient in a small champion device. our modules are currently only about 18% efficient. So we have to figure out how to improve that. So I'm going to finish the talk off by giving you a couple of examples of things that we've done to study these things. One of them is to look at this so-called FAPI material that's formamidinium lead iodide. And so it's a lead iodide cubic structure with a formamidinium ion in the middle of it. And we've used photo emission to study degradation in these materials. This is work I did with I²CNER here at Colorado School of Mines. And so we looked with photo emission at the core electrons in the material. We looked at it under red light and blue light during the observation, so we could study it dynamically under red and blue light. We could also heat the sample somewhat. And this is an example for a material that has a little bit of excess iodine in it. The blue is the ideal material that we'd like to have, and you can see that decreases as we start to grow, as we start to expose the material under low heat to blue light. Initially, we see an increase in the lead iodide signal, and then that eventually changes and we get metallic lead that forms. So that's a problem. So what we've concluded is that there's a catalytic decomposition of the FAPI material, losing formamidinium initially, and then going on to lose the iodine to form lead metal. There's also a study that we did in collaboration with Professor Adachi at Kyushu University. And so this is with methylammonium lead iodide, a similar material. And the group at Kyushu did two different deposition processes, a one-step process and a two-step process, spin coating onto a substrate and then reacting to form this methylammonium lead iodide material. They characterized the material and looked at different compositions. It's also been studied and shown that there are some deep defects in the material that are a problem. And in particular, note that there's a change in the iodine to carbon ratio in these materials for the one-step versus the two-step. And in particular, these are generally deficient in iodine in the one-step process. That you can see that the iodine is low. So my part of this was to model the Kyushu results. My student, Kara Kearney, did this in collaboration with you all, and she used a so-called WX-AMPS computer program, added deep defects to the simulation, and for the one-step material, she showed a best fit where she had those deep defects, those problem defects, all the way through the MAPI material. Whereas with the two-step process, she found that the best fit was with those defects restricted to near the junction. So her model showed that the two-stage limits defects to near the junction where they're less harmful. She connected that to the methylammonium level in the material and explained the better performance of the device. And so this is another example of showing that you need to think about the processing, the composition of what you get. So just a conclusion slide. Photovoltaics will probably be the main new installed capacity for electric generation worldwide. Most of that will be silicon-based, and it'll probably be tandems. I'm guessing that the perovskite people will get that worked out, so I certainly think it's a great time to work on perovskite materials for silicon tandems. Research continues to improve the efficiency. And one of the main things that I want to emphasize is we need many more manufacturers of photovoltaics around the world, in particular in every country of the world, because it's very expensive to ship these devices around the world. It's much better to make them where you're going to use them. And if we're going to make a significant impact on the total electric generating capacity worldwide, we're going to need an awful lot of people making an awful lot of solar cells. So finally, thank you very much. I'm now at the Colorado School of Mines, but I spent many years at the University of Illinois, and it's been a pleasure to work with you, and I appreciate you inviting me to give this talk. So thanks again, and I'll be happy to take any questions if there are any.
Yeah, thank you, Angus, for your comprehensive talk about solar cells. I really enjoyed your contents. So, okay, we can take some questions. So if you have a question, please raise your hand or provide a comment in the Q&A panel. But maybe it's easy to just raise a hand. Can you please raise your hand? Yes. Okay, soon. Yeah, please. Done. Yep.
Hello, can you hear me?
Yes.
Yes.
Okay. Thank you, Professor Rockett. Thanks for your very nice presentation. And here I have a very small question about the flexibility of this inorganic materials-based solar cells. And you introduced the silicon or some other organic materials. And so how can we solve the flexible substrates or flexibility of these solar cells compared with the organic materials?
There are a number of ways of making flexible solar cells. You can make these inorganic materials, the thin films, you can make them on metallic foils. The organic ones certainly are flexible. One of the problems that the organic materials have is that they're sensitive to oxygen and other reactive species. And so if you make them flexible, you still have the problem of keeping these gases out. And so you need a flexible encapsulation as well. Most of the time, people have not found flexibility to be that important because the majority of the applications are very large arrays of solar modules out in a field or something like that. You can make money selling small products that are flexible, but they're usually in niche markets. So if you want to make a lot of money or have a big impact, you usually don't care about flexibility very much.
Okay. I see. Thank you very much.
Sure.
Okay. Yeah, thank you. Okay. Next is Toshinori, please.
I think he put a question in the chat.
Can you hear me?
Yes, we can.
Okay, thank you very much. So I'm now investigating hybrid perovskite solar cells. So I remember you mentioned solar cells need to be manufactured fast within 10 minutes. So after film fabrication, I have to anneal perovskite films for 30 minutes, already longer than 10 minutes. So perovskite solar cells are not good for commercialization because of the longer fabrication time, 30 minutes.
No, you don't have to worry about that. So the 10 minutes is only for an expensive tool. So if you can anneal your solar cells in a batch, then it's not a problem.
I see.
So really, I wouldn't worry about that. So for example, First Solar will take a piece of glass into their manufacturing facility. 2 hours later, it comes out of the process when it's done. Most of that time is spent annealing the ethylene vinyl acetate that's used for the encapsulation. So there are slow processes in any manufacturing of solar modules. In your case with perovskites, they have some wonderful advantages because you can deposit them from solution by spray pyrolysis. You can deposit them by spin coating and annealing and so forth. So you can work with very low-tech tools by comparison. That's one of the things that makes them so attractive. So I wouldn't worry about your 30-minute anneal. I think that won't be a problem for you.
Okay, thank you. I have another question. So most of high efficiency perovskite solar cells contain red atom, PB. It's a harmful. Yep. So I talked with NREL researcher in US. So they mentioned lead-free is not required in US.
That's correct.
That's correct. Okay. So, but in Japan or European countries, so we have to remove red metals from perovskite solar cells. So
So I have two.
think,
I have two comments for you on that.
yeah,
First of all, you have a car.
yes, I know in my car, but batteries, lead is
Big,
included. Yeah,
huge piece of lead in your car battery.
yeah,
So First Solar had exactly this problem because of the cadmium in their device. And they have a very clever solution to this. First Solar says, I'm not selling you a solar module, I'm selling you electricity. I still own the solar module, my solar module. And so it's my problem. When I'm done, I will take that solar cell back and I will recycle it myself so that you don't have to worry about the cadmium.
I see.
And so in your case, first of all, for the thickness of the methyl ammonium lead iodide or whatever you're using, I think you could safely say that your solar module is 99.99% lead free because it's mostly glass. So the amount of lead is insignificant. I would also say, what I say about the cadmium telluride cells is, where would you rather have your lead? Would you rather have it in a nice clean solar cell that you know where it is and you've contained it between a couple of pieces of glass, which doesn't melt very well? Or would you rather have it in a mining site leaching into the water nearby? It's much better to have it in the solar module. So I think there are ways of dealing with lead, but I would say look at what the cadmium telluride people at First Solar did, and the fact that they don't sell modules, they sell power. That's been a very successful model for First Solar.
Thank you.
So Angus, related to this question, I have a small question. So that in case of the silicon or CIGS in inorganic materials, so the energy related to the manufacturing seems very high because of they require the high temperature processes. So I heard that it takes almost 10 years or 15 years to recover the energy used for the manufacturing. So that by taking into account such energies, so the perovskite or organic is promising. I just want to know your comment. Yeah.
Well, first of all, the perovskites are very promising to begin with. They're extremely exciting technology. I know you work on them a number of people there work on them, and I think that's a fantastic idea. Very, very likely to be successful. And so, I think the energy payback time for these other technologies is not what you're saying. I think it's between 1 and 2 years. The thing about silicon, for example, is that it takes a lot of energy to run a Czochralski crystal grower, but a Czochralski crystal grower produces a solar cell produces a solar cell worth of material every few seconds. And so, yes, it's a lot of energy, but it's also making an awful lot of solar cells. And so if you spread that energy out over all of the solar cells, my silicon solar array sitting on my roof is a 5 kilowatt array. It has made something like 13 megawatt hours of electricity in the past 3 years. I doubt that it took 3 megawatt hours or 15 megawatt hours or whatever to make those solar modules. So I think that the general feeling is that the energy payback time is just between something like 1 year for probably a perovskite cell, 1 year or less. Silicon, I think it's between 2 and 3 years.
Okay, yeah, thanks for your comment. Okay, I have another question. So Leonard, please.
Oh, okay. Rockett, this is Kwati. Thank you very much again for your talk. I think you mentioned something on the thing that was slide 24, where you had these junctions, these multi-junctions, or these junction systems being stacked together, and giving a relatively very, very high efficiency, probably 36 of them giving an efficiency of 72. Could you explain a little bit the mechanism behind this? And that would be the first question. And you also mentioned that an ideal sort of photon energy should be roughly around 1.4. So I always have this question in mind that, okay, if you have a material that is able to capture the entire photon energy region, how will that reflect to its efficiency?
So think of this sort of like a hydroelectric dam where you have a lake up on the mountain and you let water run out of the lake and you use it to turn a generator. But the rule is that the higher up the mountain you place it, the less water you have available to run your turbine generator. And so if you have a lake way up on a high mountain, you can get a lot of power, a lot of energy out of that water, but there's not very much water flowing. Whereas if you have the lake very low down, you have a huge amount of water flowing, but you get very little energy out of it. So it's the same thing here. If we have, so if I have a semiconductor with an energy gap where I've shown it here between the yellow and the green, it is transparent to all of these yellow and red photons. We lose them. We don't get any current out of them. We get voltage out of the ones that are above in the green and blue. But if I have, let's say, a 3 electron volt photon, and it takes an electron, and I have, let's say, I have this band gap at 1.4 electron volts, and it absorbs a 3 electron volt photon, my electron comes out way up in the band, and it loses a lot of energy, relaxing down to the 1.4 volt band edge. So I waste all of that energy that's above the gap. So yes, I can get a lot of current out of this device because there's a lot of photons in the green part and the blue part, but I lose more and more energy. The farther up in energy I go, the more energy I'm losing as I come back down to that 1.4 volt gap. So what I'm going to do is I'm going to have a wide gap solar cell on top of it that gets a lot of energy out of the blue photons. So I'm just barely capturing the blue photons. I'm not getting a lot of current, but I'm getting a lot of energy. Then underneath that, I put another solar cell that catches the green photons, and another one under that that captures the yellow photons. I'm not getting a lot of current out of any individual one of these devices, but I'm adding the voltages that I get from each one. And so what you get with a multi-junction is you add the voltages of each of those devices. So in our silicon perovskite tandem, we have a high efficiency perovskite material, which is collecting the blue photons and letting the red and the yellow photons through. And those are being captured by the silicon. And you can actually see this in this chart down at the bottom here. This is a so-called external quantum efficiency chart. The blue curve here is from the perovskite solar cell, and the red curve is from the silicon. But the net result of the two devices is this orange curve, which shows that you're collecting all the way across the solar spectrum, from way out at the long wavelength band to way down at the short wavelength band. And so each of the two individual cells produces, we design those two energy gaps so they produce the same amount of current, and we add the voltages because the devices are in series, the voltages add at constant current.
Oh, thank you.
Okay, thank you. Okay, we have another question from Hiroshige. Please.
Hello, Angus. I'm Hiroshige. So I'd like to continue the question for your multi-junction type solar cells. So I'm quite interested in this technology because this technology will increase the efficiency, efficient energy conversion, the efficiency per area of the cell, correct?
Yep, that's right.
Yeah, in this case, you showed the reduction of the cell processing cost, but also the solar cell needs the area to install the solar cell. And particularly in Japan, the cost of the land, cost of the roof is quite expensive. So the increase in the efficiency will be much more convenient regarding the cost for the area of installation. So in this case, I hope this technology will be advancing much to increase the efficiency for the cell. And in this case, can you have more prospect of this kind of cell, multi-junction technology?
If you can make the perovskite cell in the combination that I show here, if you can make that perovskite cell stable,
yep,
you will be able to make a fantastic module, because the champion device is almost 30% efficient. That's better than anybody has made in any single junction.
Mm-hmm.
And the perovskites are relatively easy to make. They're amazing materials, especially if you can combine them with something like spirometad or PCBM, something that you can evaporate or spin coat or whatever. Could be an extremely inexpensive and low-tech device to manufacture. Put it on top of your silicon device and there you go.
Yeah.
But you have to make it stable. That's the hard part.
Mm-hmm. In this case, it is not so difficult to install or make it. So what about more number of layers, particularly for the feasibility to the commercialization or social deployment?
If you can make a triple junction cell, certainly it would be worth considering. So silicon has a band gap of about 1.2 electron volts. The two junction combination that goes well with that is about 1.7. And the perovskites can do that relatively easily.
Yeah.
And so to introduce something in the middle, you'd probably want something maybe around 1.4 electron volts. So the cadmium telluride cell or something like that potentially could make a triple junction device.
Yeah. So what about the higher band gap material on the top? For example, 2.5 dB, 3 dB.
You don't gain very much. The problem is that you have to match the current. If you stack these devices up like this, you have to match the current. So it's the same amount of current that flows all the way through the stack from the top to the bottom.
Right.
And so every solar cell has to make the same amount of current. And there just aren't very many photons in sunlight above about 500 nanometers. Sorry, below 500 nanometers. So the problem that you have is with this solar spectrum, that now you're out here in the upper range of this blue spectrum, and you won't have enough photons.
Okay, I understand. Thank you.
You can do it. That's if you do that, then you have to chop the rest of the spectrum up into lots of little pieces.
Right.
So that's where you get into a 6-junction cell, for example. But now you're getting into a problem. So one of the tricky parts that I didn't really talk about is how do you make an electrical connection that's transparent from the bottom of the perovskite to the top of the silicon. In this case, with silicon, it's relatively easy because you say, well, okay, I can make indium zinc oxide or something like that, and that'll make a contact to my PCBM and to my P-type silicon, so I'm good. The problem comes when you start saying, now I'm going to stack, let's say, a series of perovskite cells of different gap on top of each other. Each one has to survive the processing of the one underneath it or the one on top of it. And so I have to be able to process all of these different devices without damaging the ones that are already there. This has been a big challenge for the multi-junction 3.5 community, but they did figure out how to do it.
Yeah.
But Yeah, so 2 junctions to start with. If you can
Okay.
do 2-junction perovskite silicon to start with, don't worry, you'll have a very successful product.
Yeah, yeah. I understand. Thank you.
Mhm.
Okay, thank you. Oh, okay. We have yes, Professor Ishihara, please.
Sorry. Can you hear me?
I can.
Okay. Hello, Angus. This is Ishihara. And then
Nice to
I will,
talk to you.
yeah, good evening. Yes. I just ask you on the simple questions. First one is on the perovskite type photovoltaic cells. Its efficiency is increased dramatically recently. But for me, if comes almost a saturated level around the 25 or 27. Therefore, I just ask you, what is the theoretical limit of the efficiency of these perovskite solar photovoltaic cell?
Well, that depends on what the energy gap of the perovskite is. So if you can make a perovskite with a 1.4, 1.45 sort of EV energy gap, then you'll probably hit something like potential of 37% efficiency in 1 junction. Gallium arsenide is about that same energy gap, and it has only achieved about 27% efficiency. So I think it will be difficult to keep pushing these perovskites higher than 26, but if you can make them stable, a 26% efficient solar cell that you combine with a silicon solar cell, you can make a 1.7 EV gap cell at 26% efficiency routinely and stack it with a silicon cell routinely. I don't think you'll have any problem until somebody comes along and figures out how to make a triple junction or something.
Okay.
But that's.
And then, yeah, this question has just come from the perovskite cell is quite high resistivities, I think, because it's organic types. Therefore, I wonder there's some limitation. Although the band gap comes to the quite nice level, but because of the resistivities, it has some limitations. That is my question is coming. And my second question is this related with some toxicity of the perovskite. They use a lot of not only the PV, but also the halogen. Therefore, halogen also quite toxic to the natures. Therefore, I just ask you, is there any environmental compatibilities because of the halogen compound? And my second question is how stable of this perovskite? What is the feeling? According to Professor Adachi's result, it increased the stability dramatically, but there has some still limited. Therefore, I wonder what is your expectation to stable for some period? Yes.
So the stability has improved dramatically, and I think that's really a question I would let Professor Adachi answer, because I think we have made tremendous progress on stability of the perovskites. My concern with stability is this business of the sort of catalyzed photodegradation. In the case of what we saw with the FAPI material, you could have a perfect encapsulation, and if you have excess iodine, it could start the catalytic decomposition, and unless the material would be reversibly able to form again, if you could get it to go back the other way, which you may be able to, stability may be an intrinsic problem for some of these materials. But there has been a tremendous amount of progress in recent years on stability of the hybrid perovskites. So I have a lot of confidence that it will be solved. And so that's certainly, I think, not going to be a big issue in the long run. It may take a while, but I don't think it'll be a big problem. In terms of the halogens, the manufacturing community is used to dealing with these compounds, and you just have to be careful and you have to be safe. And the main problem for countries like Japan and the United States, which worry about that sort of thing, is the Chinese who don't worry about that sort of thing. And they ruin their land, but on the other hand, they make something with some horrible chemical in it, and they may have a problem, but they have a market selling it. So I think you can deal with these halogens. Bromine and chlorine are not very nice, but we deal with these things all the time in chemical labs. So I think that can be managed. The stability is a challenge, but I think that will probably also be managed.
Thank you very much.
I'm also very optimistic for the stability issues. So just controlling the ion migration, suppression of migration, increase the stability issues. Yes.
Yep.
Okay. Yes, Toshinori, please.
So I'm Toshinori. I have one more question. So about tandem solar cell architectures. So you mentioned the tandem solar cell architecture of silicon and perovskite. What do you think perovskite tandem architectures? So I put the wider bandgap perovskite, smaller bandgap perovskite on top of the smaller bandgap perovskite.
So yes, you can do that. And it comes down to what range of energy gaps can you reasonably make the perovskites and still have high efficiencies. Go ahead.
I usually use the perovskite with the bandgap of 1.5 eV. So we can make the smaller bandgap perovskite. The bandgap is 1.2 or 1.3 eV. So we put these two different bandgap materials to make a tandem solar cell architecture. So I think the silicon part is not flexible and silicon part is very thick. So if we can make perovskite tandem architecture, so we can get flexible, high efficiency, and very thin tandem perovskite solar cell, all perovskite solar cells. So
that sounds like a. Sorry.
Okay, I think that structure is promising for future commercialization.
So that's a great idea. For the 1.5 EV gap, 1.2 EV gap, that's really
that's right.
2 of 3. That's sort of 2 out of the 3 you need for a triple junction. So the you want something for a 1.2 EV gap. In a tandem, you want something more like 1.7 EV gap to match the currents.
I see. I see.
So with 1.2 and 1.5, you're going to be in pretty good shape for a triple junction if you can then go on and make something more like 1.7 or 1.8 gap.
Okay, I see. Yeah, I can fabricate wider bandgap perovskite easily. 1.7 or 1.8 is possible to make.
There's a standard set of energy gaps for a triple junction. I don't remember them off the top of my head, but if you send me an email, I'll be happy to look it up for you. But there are standard current matching conditions for a triple junction. And your current materials in the 1.2 and 1.5 EV sound to me like the sort of low gap and middle gap of a triple junction.
I see. Thank you very much.
Can you currently stack your material? Can you make these solar cells on top of each other and have them all stay as you fabricate the device on top? Can you make it?
Yeah, I'm not trying to make, but we have to use the solution processing. So it's very difficult to prepare the top perovskite layer on top of the bottom perovskite layer by solution processing because of the dissolution of the underlying perovskite solar cell.
Yep, I would guess that would be the problem. So that's the trouble with any multi-junction is that you have to have a stable bottom cell, and That's why the silicon perovskite tandem is so attractive, because the silicon is not going to go anywhere.
Therefore, I have planned to make the bottom perovskite layer by solution processing and the top perovskite layer by vacuum deposition or something. But vacuum deposited perovskite solar cell have very still low efficiency. So that is a problem. Okay, thank you very much.
Good luck. It's a good research problem.
Yeah, that's right. That's right.
Okay, no more questions from audience. Oh, okay, thank you very much for your active questions. And so before closing this session, so fortunately, so the Petros is now online, and I'd like to ask him to give closing remarks. Could you please, Petros?